And now we discuss properties of the continuous time Fourier transforms. And a note is made that they are similar to those of Laplace transform. They are discussed in section 3.4 of the text. So it is assumed that you have already met the Laplace transforms in another unit, and I think we have already agreed that. In CNT 2, we must have met the Laplace transforms. So we delved straight on to the properties. The first property is that of linearity, such that if we have two non-periodic signals that you add them, and when you're adding them, you multiply them with a constant alpha a1 and a2, then this is equivalent to Fourier transforming one and Fourier transforming the other individual, and then you add the result. Later. So if you are to do a Fourier transform that is as a result of addition of two signals, the linearity principle or property would definitely tell you that the resultant is individual Fourier transform multiplied by the constant that you applied to the individual time domain signal x of t. And the second property is that of time shifting. And of course, you can see that if you shift your time domain signal by t naught, this is equivalent to shifting the phase of your Fourier transform by j omega t naught, or rather by omega t naught. And therefore, it's like it's like a linear term is added to the original phase spectrum of your Fourier transform. Frequency shifting is very comparable to time shifting, and they are comparable because the two of them are said to be dual or follow the concept of duality. And if you look at the frequency shifting, we are saying that a multiplication of the frequency time, sorry, the multiplication of our time domain signal x of t by a complex exponential signal ej omega naught t is called, or sometimes called, complex modulation. And thus, we normally say the following, that complex modulation in time domain is equals to the frequency shifting in frequency domain. And just to illustrate that, you are doing complex modulation on the time domain, and you are shifting the frequency in the frequency domain with a frequency that is equivalent to the phase that you introduced in a time domain. Now, to compare the frequency shifting with the time shifting, we simply say that a shift in time is equivalent to a linear phase shift in frequency. So you can see that we are shifting our non-periodic signal or periodic signal in time domain with the time t naught, and we are on the other hand, we are introducing a linear phase shift that is defined by omega naught t or omega t naught. So those two are very significant and they are very similar. You just need to remember that if you multiply, if you have a shift in time domain, this will result in linear phase shift j omega naught t or j omega t naught that you developed here. That simply tries to introduce a phase shift in your frequency component or frequency or Fourier transform of your frequency component. And on the other hand, if you actually state that the Fourier transform is now shifted in by omega naught, this is going to bring ej minus omega naught t to your x of Fourier transform x of t. And therefore, those can actually be stated as such, and you can see that a shift in frequency is very similar to the frequency shift in time. One is in the time domain, which is this one, and the other one is in the frequency domain, which is this one. Therefore, they are following a very similar trend, as you can see. Another important property is that of time scaling, whereby we are introducing time expansion or compression in time domain, and it results in two changes in our frequency domain component. And we are saying that this property follows directly from the definition of Fourier transform. And we say that equation 552 indicates that the scaling the time variable time variable t by the factor a, which is equivalent to compression if a is bigger than 1. We're saying that if a is bigger than 1, this is equals to compression. And if a is less than 1, this is equivalent to expansion in time. So if we compress our signal in time domain, we receive an inverse scaling of the frequency variable omega by 1 over a, as well as the amplitude scaling by 1 over modulus of a. And thus, this property implies that a time compression, which means that if a is bigger than 1, the time is compressed, results in spectral expansion. You can see if you compress time, you expand the spectrum that is defined by omega. And similarly, if you expand your signal, that results in the spectral compression. And I think if the best thing would be to look at this example literally. So here I've just brought in some diagram to illustrate how the compression and expansion works. And I have brought in a signal having a period of 2. If this is considered to be in time, then 2 where we count 2 as the angular frequency of the first signal x1 of t, because you normally say that the angular frequency omega 1 is normally given by 2 pi over 2 or over t naught. And if you consider that my t naught here is equals to 2, then you are going to find that 2 pi over 2 is going to give us a pi. And therefore we can actually say that our signal x of t, x1 of t can be represented by sine of pi of t, and we are giving that as omega 1. And if we look at this other signal, you try to estimate, it will have a period of, this is half a period, and therefore the period is actually 8. I think this is correct. So the period is considered to be 8, and therefore we are going to say that the omega 2 of this x2 signal is simply going to be found from 2 pi over 8, and of course that becomes equivalent to omega 2 is equals to 0.25 pi, Therefore, we can say that this is inaccurate. It's actually going to be represented by sine omega 1. If you just do some mathematics expressing omega 1 in terms of omega 2, you say that omega 1 is equals to pi, omega 2 is equals to 0.225 pi. Then try to express omega 2 in terms of omega 1 with our compression or our scaling factor A there. We actually find out that omega 1 is expressed as 4 omega 2, and therefore because we wanted to find the value of omega 2 in terms of omega 1, we actually find that our A is equals to 1 over 4. And as you can see, this signal is expanded in time. Therefore, we are saying that when you expand a signal in time, or rather when you expand a signal in time, when A is less than 1, as you can see, our A in this case is less than 1. When you expand it in time, then this results in a spectral compression. So if you are now to draw these signals in frequency domain, you'd actually realize that the spectral component of this signal x of t is compressed, whereas the spectral component of this x1 of t is expanded. Another very significant property is the one that we refer to as the time reversal. Time reversal says that if you reverse time in time domain, you get a similar reversal in the frequency domain. And this can be obtained by introducing in what we have just done above, where we said that x of at is equals to 1 over a magnitude x of omega over a. Therefore, if you say your a is equals to 1, what you are going to minus 1, that means that your x of minus t is equivalent to minus x of minus omega. So that is what time reversal tells us. Of course, this minus 1 is lost because we are saying the magnitude of this or the absolute value. Therefore, we don't have this apologies for that. So we definitely have x of minus t is equivalent to reversal in the frequency, which is expressed as such. Again, we introduce the concept of duality, which is another property of Fourier transforms. It is also called the principle of, or the property of symmetry. And we say that if you have your time domain signal x of t, it may be transformed to 2 pi. I think here again, I want to rectify myself and say that we are considering interchanging these parameters. Ordinarily, we say that x of omega transforms to x of t, and you see this is a Fourier transformation. But if you have a Fourier transform already, but if you change it from being a function of omega, and now you want to find its equivalent in time domain, there is a change that you do which simply says that you'd lab or clear the omega and clear the t. And if you now introduce your t there, you're going to introduce another term here that is 2 pi. And instead of putting x being as omega only, you introduce minus omega. So this is now no longer Fourier transform. It becomes the concept or the property of duality or symmetry. So similarly, we talk about the differentiation or the differentiation property. we ask ourselves, if we differentiate our signal in time domain, what happens to its frequency component? And we are saying that we just introduce a j omega to its frequency component. And therefore, if assume your signal is sine of omega t that transforms into, oh sorry, this is supposed to be omega naught. So assume you have your x of t that transforms into x of omega, and you're saying that I should actually write them at a space where I have a space. So I want to clear up this space so that I can write without really interrupting myself too much, sufficient space. So I'm saying that you have x of t that Fourier transforms f of t into x of omega, and we are considering an example of sine of omega naught t that Fourier transforms into this, how we normally get Fourier transform, by the way. Fourier transforms into actually I'm now writing for you the real Fourier transform of sine omega naught t, supposed to become minus j pi of del of omega minus omega naught t, of course without the without the omega, without the t, so rather, then minus, actually this is the real Fourier transform of sine omega, omega minus plus omega naught. So if that is your Fourier transform and of our x of t, our d dt of sine of omega naught t is actually equals to cos of omega naught t. And therefore, without wanting to know the Fourier transform of this new function cos omega naught t, we can just say that the Fourier transform of this derivative, we will just introduce this j omega to our Fourier transform that was minus j pi, and then we keep other terms as they were, minus del of omega naught plus omega naught, not omega naught plus omega naught, rather omega plus omega naught. Sorry. Yes. So, and therefore, if we saw and if we solve this, this should come to negative j times j times j is actually equals to 1. Therefore, we are going to have of course, I need to correct myself again that this is not true. We know minus j, or rather j dot j is equivalent to root of minus 1 dot root of minus 1, and this is the one that gives us minus 1. Therefore, if you introduce a negative there, this will become what am I saying? I'm saying that this will become root of 1, and therefore it will become positive. And therefore, when you introduce a negative, then this will become negative 1. And therefore, we introduce a negative 1 to this part. We get this becoming positive. And again, as a correction, I introduce an omega naught that I forgot here. I can see some mistakes here, and I think I beg your pardon. I need to rectify some of these things, because sometimes when you do something in hurry, you are about to make mistakes. This cannot be resolved the way I have solved. So we are saying that j dot j is equivalent to root of minus 1 squared, and that is equivalent to minus 1. Therefore, when you introduce a minus there, this becomes a plus. So this by itself is going to become a plus 1, and that goes just like I had said in the beginning. So what we are left with is bringing in this term, which is omega pi d omega minus omega naught plus del of omega plus omega naught, and that agrees with our definition, which says that in this case we can put we can actually say that this is equivalent to the Fourier transform of this, which has omega at this one. Therefore, this is actually still our omega kept at that point. So we agree that this equation 5 agrees with what it says, and we have just done a demonstration, although we have struggled making mistakes here and there, but finally we have shown that Fourier transform of derivative of sine of omega naught t is going to be equivalent to Fourier transform of omega naught cos omega naught of cos omega naught t, just as we have indicated here. So if you actually look at the details for the definition of the cos of omega or the cos of omega naught t, it will definitely give you this, and now our omega naught agrees with this omega. So in a similar manner like we have done with the differentiation in the time domain, we are saying that if you want to do differentiation in the frequency domain, and you know the you know your Fourier or inverse Fourier transform of your x of omega, then the only term that you need to do is to get your Fourier, the inverse Fourier transform of your x of omega, which you obtain to be x of t, and then you multiply that by j of t, and that will give you your solution. Another property is that of integration in the time domain, and it says that if we have our function in time domain x of t, and we require to perform, we know its Fourier transform to be x of omega, but we require to perform the integration in time domain. So we want to find out what will be the result of its Fourier transform, and we are simply saying that the result will be equals to the Fourier transform of the signal itself evaluated at omega is equals to 0, as you can see here, multiplied by the impulse response of omega, multiplied by pi, and then the other component that we introduce, or which must be there, is that we are differentiating with 1 over j omega. So remember that when we are doing the differentiation, we are introducing j omega. Now, for the sake of integration, we are saying we are going to be dividing by j omega, and therefore you have your original signal that you would have got in frequency domain. And we are saying that this term is considered to be the DC component in the integrator that would be available once you perform the integration. So that is why we introduce this that component, and therefore we are able to have to evaluate Fourier transform under the integration in time domain. We have already met the concept of convolution, and there is a statement that we have said in the past, and that is the one we are going to repeat. And it says that convolution in time domain becomes multiplication in the frequency domain, and vice versa. So that is what we are saying here in question 558, that convolution in time domain is equivalent to multiplication in frequency domain. If you do it the other way round, it says that convolution in frequency domain will give you will be equivalent. So this is inverse Fourier transform, will be equivalent to multiplication of x1 of t in time domain times x of x2 of t. So we refer to this statement defined by equation 558 as time convolution theorem, and this property we refer to it as frequency convolution theorem, and that takes us to the one that is defined at this point. Of course, we observe one difference that is very particular, that in the equation that I have just introduced, we always introduce 2 pi at that point, or you can divide both sides by 2 pi and by 2 pi, and the frequency convolution theorem stands as defined in equation 559. And now we mention some additional properties of Fourier transforms, and that we are considering our signal x of t as real, consisting of two components, even part and odd component. And we are saying that if that kind of a signal will have Fourier transform x of w, or defined by x omega, which has two components, the real component and the imaginary component. And if this be the case, then we are saying that equation 561 is the necessary and sufficient condition to show that x of t is real. So if you if you perform a Fourier transform of a signal that does not satisfy this condition, then you actually realize that your function x of t is not real, and it was it was complex, or it was having some imaginary components. But if this condition is satisfied, then we are saying that we can be able to break our Fourier transform, such that the real part of a Fourier transform gives you the even, or the Fourier transform of our even component of our time domain signal, and the imaginary component of our Fourier transform gives you the odd part, the Fourier transform of the odd component in time domain, this one. And therefore, that's a very important realization, that we can always be able to break you can be asked, find the Fourier transform of the odd component of your signal that is defined by xt. And if it satisfies this condition, then we only need to look at the imaginary part or the real part to find the Fourier transform of the odd component and the Fourier transform of the even component, respectively. Last but not least is the Parseval's relations among the properties of continuous time Fourier transforms. And the Parseval's theorem is derived from equation 562, that says that if you have two signals x1 and x2, if you evaluate the Fourier transform of x2 and then you integrate the x1 over x2, you are going to find the Fourier transform of the first signal integrated or multiplied with the original signal x2 integrated over the same interval. And therefore, the most important relationship that we should get is equation 564. And this equation is called the Parseval's theorem. And it says that, remember we met Parseval's relation or Parseval's theorem in the Fourier series, and it was similar to this, except that now this one is for the non-periodic signals, or rather a generalization of the non-periodic signals. And therefore, we are saying that equation 564 is called the Parseval's identity. And we notice that the quantity on the left actually allows us to determine the normalized energy quantity of our signal in time domain x of t. And it says that, or this identity says that, if you want to find the energy content of your time domain signal x of t, you can also be able to obtain it by integrating the Fourier transform of your signal, and then of course squared over all the frequencies. And for this reason, this term here is referred to as the energy density of our time domain signal x of t. And now this relationship again is also called the energy theorem, just to because that is what the Parsifal's theorem states. That it states that if you want to find the energy contained in your time domain signal, you can be able to obtain it by first of all finding the Fourier transform of the signal, and then integrating it over the infinite period, and as defined in equation 564, you are able to determine the amount of energy contained in your signal x of t. So in summary, we have gone through about 13. We have gone through about 13 or so properties of Fourier transforms, and they are summarized in this table. And just to highlight, we say that if you have your time domain signal x of t, it can always be transformed using the Fourier transformation to get x of omega. And therefore, similarly, your x1 of t becomes x1 of omega, and x2 of t becomes x2 of omega. These two are going to be useful in explaining the other concepts that we have already developed. The first concept that we discussed was the linearity, that says that if a1 x1 plus a2 x2 can always be transformed to have a1 x1, which is the Fourier transform multiplied by your scalar a1 plus the scalar a2 multiplied by the Fourier transform of x2. And we also dealt with the time shifting property that says that time shifting in time is equivalent to multiplication of your Fourier transform with the complex exponential ej omega naught t naught. And again, we also we compared those two, and we said that if you have complex modulation in time, it is equivalent to Fourier, or to shift in frequency in Fourier transform. And then the scaling talked about the concept of expanding your signal in time domain. It is equivalent to compressing its spectral or its spectrum in frequency domain, or rather, if you expand your signal, then you compress. If you compress, you expand the Fourier component, the spectral component of your signal in frequency domain. The time divisor said that if x of minus t, you are going to get the reversed Fourier, the spectral component in the negative direction. And the duality also said that you can be able to obtain your, if you actually transform. We did this together, so I don't need to repeat all that. We also did the time differentiation, that we introduce a j omega component. The frequency in differentiation, again, we introduce the j omega minus jt component on the time domain. And then we did the integration where we introduced this constant that we called it the DC component after dividing our Fourier transformation with j omega. And then we said the convolution in time is equivalent to multiplication in frequency, and multiplication in frequency is equivalent to convolution in frequency, except with the introduction of the division by 2 pi. Last but not least, we say that if you have a real signal that has an even and odd component, then you can be able to transform your signal and be able to develop to generate or to identify the real part. Gives you the even function, or the Fourier transform of your even function in time domain, and the imaginary component gives you the Fourier transform of your odd component in time domain. And last but not least, we talked about the Pasivos relations that gives us the amount of energy contained in a signal that can be evaluated over all the frequencies over which the spectral components of the signal span. Table 5.2 is here to show us some of the common Fourier transform pairs that you can meet, particularly when you are dealing with signals. I'm not going to delve much into this. We have only met, I guess, these two so far. And what I would say is that some of these are worth remembering, that the Fourier transform of an impulse unit impulse signal is always going to give us a 1. If you apply the time scaling property, you are going to have the complex exponential introduced, which is a factor of the scaling, etc. So I would actually need you to try to memorize this one, because they are very important properties that you are going to be using more often than not, particularly when you are dealing with signals like we are doing now. So I think I will stop at that for this section, and then give you some time to memorize and try to figure out how some of these things are coming about. Always be able to identify what kind of signal you are dealing with. Probably you might also need to identify some signals that we may not have discussed yet. This is called a signum function, and I think we have also met with another one that we never met called lamp function, if I can be able to identify it. So I think it's not represented here. Oh yeah, the ramp function. Well, it may not be exactly that. So I think I will give you some time to look at this, and then we are going to proceed to the next section in 5.5.